Hi, so I'm recording this after recording the whole video, and I missed saying a couple of things. First, if you're coming from a different engine, I know it's gonna be tricky. If like most of this stuff, I guess you could adapt because it's just like what you want to learn is the principles and the concepts. So you can do like easy, like quote unquote easy IK animations. Godot, like the animation player for Godot allows to do some interesting things that maybe, or I don't know, you're just gonna have to adapt for your engine. You're also, it's gonna be important for you to know a little bit of vectors, trigonometry, not that much because even I don't know that much. I've just learned how to adapt it here. I'll show you some references to, for example, like the coding train, which is a really great channel for understanding vectors and a whole bunch of concepts. I also linked the inspiration for this IK, which is another Godot video. He's doing a spider. I'll link that video up on the description, and I'll try to include a couple more videos like learning about basic trigonometry, specifically for game dev. And please pardon my explanations because I'm fairly new to this, both YouTube and game dev. So I'm not an expert here. I'm not claiming to be an expert. I'm just sharing my experience and what I've learned, and hopefully this is useful for someone else. Let's get started with the video. So the first part is gonna be, we're gonna look at the variables that we need, and this is just the way I've set it up. The actual algorithm for the IK may use a lot less. Okay, let's get started. So first I have a bone class. This is just for like easy access within the editor. Just so I don't have to be guessing or remembering all of these properties. To kind of tell you what that is like this is the start and this is the end. And the sprite, it could be whatever you want. The length, we're just gonna calculate that. We're gonna pre-calculate it, so we don't have to calculate it every frame. If your bones are gonna change size within animations, which you could, you're probably gonna want to calculate this length as part of the algorithm. But I just pre-calculate it, and if I reset the bones, I'll just reset the whole calculation. Angle is just used just as a helper function if I want to get the actual angle of the bone. The inner angle is the inner angle, because the end, let me just show you what I mean here. So suppose you have this bone here and then the end is a child, which is here. Sometimes you set the bones to be something like you have your start here, you have your end here, and so your sprite maybe goes like this, I don't know, something like that. But sometimes maybe your sprite is vertical like this, so you want to set up your end node here. So there's an angle between the end and the start. Here would be 0 and here would be 90 degrees. So depending on how you set it up, you're gonna get a different inner angle, and we need to know that for the IK calculation. And this normal, it's just like angle, so it's just a helper function. We don't really use it from the IK. It's just in case I want to know from outside what's the normal. Because of the algorithm that we're gonna use, you cannot really change the amount of bones. So it's not like fabric, which is you probably heard about that one. So the difference, I'll explain this real quick here. So you have, say you have your first bone here, and you have a second bone here, and with like a leg, that's all you need. The foot, for example, or the hand, if this is an arm, that one you don't really want it to be part of the IK, because if you think about it, if suppose this is a wall and you want your arm, if you have fabric and you want to reach this wall, your fabric may end up looking something like this, like this being the hand, but it's always gonna reach with the hand. But what you want, for example, if you wanna touch the wall, what you want is your first two bones to actually reach it, and then you might want your hand to look like this, so it's like leaning against the wall. And if you wanted to look like this, you could, like, you just have to like offset the end of the IK, so you can offset it to the length of your last bone. But you have a lot more control for like running animations and grabbing to surfaces. It's much better to do 2 bones and then rotate the last bone accordingly. Okay, and the way this algorithm works is we have the like bone A, which is this variable here, and then we have bone B, which is the next one. Of course, we're just going to ignore C. And then if the target is here, all you need here is to calculate a triangle like this, right? And then the way we do this is we use the side-to-side calculation, which is a way of calculating all of the inner angles of a triangle when you already know the lengths of all of the sides. So if you know side A, B, and C, you can figure out with the law of cosines what the angles are. What's good about this is that you don't need to iterate like in Fabric. It's immediate and it's precise. So you just do one calculation per frame and that's it. And it's easier because you control how this, because with Fabric you don't know, like if you have a leg like this, sometimes with Fabric your leg might actually go the other way, and that doesn't really happen with a leg or an arm, and you don't want those like accidents, and you want to be able to control that. And you can do it with Fabric, but it's a lot more complicated. Here we have a variable called direction, and this direction basically multiplies the angles that we calculate by either 1 or -1, and that will flip this triangle to the other way. So that's what we're doing. That's the algorithm that we're using. Okay, so let's move on with the variables. So the direction, as I mentioned, that's what it's gonna do. Follow is just if you wanna activate or deactivate the chain. Offset, we use this offset in case we want to, if we have the target suppose at the floor, but we want to offset it by 20 pixels because that's the height of the foot, then we use the offset to do that. The root, this is like just a reference to the root of the body or of the chain, and in this case I have it set up here as the body because the reason is if your game flips the body when you go left, if you want to walk to the left and you're using scale to flip everything horizontally, we need to know that. We get it from the transform of the root, which is not the direct parent of the chain, because I have the chain here and its direct parent is this node, but we want to get the actual root or whichever node you're using to do the flipping. So if you're going to be flipping the hip, just use that one. Here I'm just getting a reference to all of the nodes that will become the bones. So as you can see, I have a bone A and an end of a bone A, and I do the same for B and C, and I also need a target node. So this is just basically when you're going to select a target, you just tell it which node is going to be your target. It could be a position, whatever you want. Okay. These variables are just for debugging purposes. So you can draw the bones, you can draw the target, you can see the bones in game, and you can see the target in the game. So if you don't have sprites, for example, and you want to draw the bones, it will draw a line on the bones. And right now it's kind of messed up because I have the rotation of the direct parent at 13 degrees, and that kind of messes up the drawing. It doesn't mess up the IK chain, but it messes up the drawing because I didn't really pay that much attention into the drawing functions, because you have to offset the rotation of the parent there. But you can fix it if you want. I don't use this that much, so I just kind of left it like that. Okay, Here, okay, this one is actually important. The lerp rate and the lerp range. What we're doing those for is if you and I'll explain this in code how we calculate this, but when the target is close, in this case the lerp range that I have set up here is 100. So if it's like at 0 pixels difference, like we're already at the target, the way the chain follows the target, it's immediate. As you can see, it doesn't like it doesn't take time to get to the target. It's just immediate. And the farther I get away, the more it will take to get to the target. I'm not sure if you can see it, but when I go down fast, it doesn't really follow as fast as when I'm close to it. That's what we're using, lerp rate and lerp range, and you can manipulate that just to see how slow you want it to follow, or if you just want it to be super like fast, then don't worry about those. These last variables, these are for the rotation. So instead of rotating like the foot directly, as you can see, this is like C rotation degrees, because this is for the last bone. So instead of rotating it, if I have the chain here and I have the foot, I don't want to come here and do like the rotation directly. We don't want to do that, and as you can see, it just lerps back. So what we're doing instead is in the actual chain, in the actual chain, we have a rotation degrees and a rotation offset. So I can set this to 30, and then I can offset it by 10 or by minus 30. It should go back to 0. And the reason we have this is because, as I mentioned before, when you're doing an animation, for the animation itself, you want to use rotation degrees, and then for the procedural stuff, like adjusting to the floor angle and all of that stuff, what you want to do is use the offset. So your animation always looks the same, but it just offset it to a different angle. And I have here, the reason I have minus 80 to 180, minus 180 and 180 is because that's what Godot uses. When you get a vector and you call its angle method, if you check the whole way around, it will always give you minus 80 and 180. So I just figure out, like, if that's the way they're doing, I guess that's the way I should do it as well. So that's the way I have it set. Now this max and min rotation, what it does is limit how much the foot can rotate, but it's only when it's using the offset. So if I set this constraint, it will activate the limits. So if I set between 90 and minus 90, the rotation itself, it's not limited by that, so I can go anywhere. But if I'm using the offset, it's not gonna go past minus 90 or 90, regardless of what the C rotation is. It's just like the sum of these two shouldn't go past those limits. And this is just in animation. Sometimes your raycast may detect like a wall, and that will like try to flip the foot like all the way back, and it will look super weird if you don't have like limits. So this is just like so you can constrain the way that looks if you happen to encounter like this weird angle. That's what that's there for. Then we have just the initialization of the bones, like the pseudo array of bones, the variable to hold the root node. Then we have this the flip vector, which is where we actually get here's where I store the transform x of the root. So when I'm flipping horizontally, this is actually changes to -1 on the x, and the y just stays at 1. And then we use this to multiply the positions and other stuff, just to make sure that it works correctly. The target node, we're just using this to store the actual reference to the node. because with the node paths you just get the path, and here we store the actual node. Total length is the length of the chain, so is the bone A, the length of bone A plus the length of bone B. C doesn't really count. The minimal distance is how much the chain can reach back onto itself. So if this bone was short, it couldn't reach past a certain point, so that's where we're using that, and I'll explain that more in detail later. Ready is used just because if you have a missing bone and you don't have a length there, your calculation is not going to be right. So we don't do anything until we're sure that we have all of the bones that we need. The distance to the target and the remaining distance to target, basically the first one is what's the distance to the target from the root, so from here to here, and the remaining distance to the target is the distance between the end of the chain and the actual target. So here this would be 0. So those would be the variables. So now let's move on to the actual functions that we're going to use. Okay, so for the functions, what we're using is the law of cosines, which I learned from a different video, and I'll link to it, which is he's making a spider, and he's using, the reason I did this whole thing is because he was actually doing a 3-bone chain, and here I'm doing a 2-bone chain, and I just needed to adapt it for my needs. So you can watch that video, but basically we're using the same thing. It's law of cosines, which is the way we calculate triangle angles once you know all of the sides. And I'm not using the angle C because we don't need it in this case, but we're using a side-to-side calculation. And here you can see that the explanation on the other video, but basically what we're doing is we pass the length of all of the sides to the triangle. Then we pass the direction, so the way we want the IK to bend. So if we want it to bend like this or like this, this would be, I'm not sure right now, but this would be 1, and this would be -1. We pass that information there, and then we do the law of cosines for angle A, we do the law of cosines for angle B. This stuff comes from math books or math articles on, you can Google that, how that works. I'm not an expert here, so my explanation wouldn't really be that great, so I'm going to spare you on that, and feel free to ask on the comments if you have questions. Okay, so that's the math stuff. Nothing really new there. Then, so what we do for initialization, or like our init function, as you can see, I have this separate from the actual ready function because sometimes you want to call it manually, and you also want to call this if a bone changes. So we have setters for every single bone. So all of these functions do the same thing. All they do is assign the node path and call init, right? As you can see down here, they all do the same thing. They just assign the value they're supposed to do, and then they just call init again, so you can recalculate the whole chain. And the init function, what it does is it checks to see if all of the paths are valid, then we assign them to the variables that we have set. So here, if the path to the root is valid, we assign it on the node. Do the same for the target. Then we reset the total length. This might not be necessary, but we just reset the length just so we can have like a fresh length at the end of this. And then here I want to make sure I have everything, and if I have one missing bone, I'm not gonna call ready. I'm just gonna keep ready at false, and then we assign it into our bones variable. So at bones A, we get the node A and the end of bone A, and the minimal distance, it's the way it's calculated, it's the length of the first bone minus the length of the second bone. And a brief explanation on that is, if you have like bone A here and your bone B is short, the minimum distance that it could follow like within its root would be like, if you were to rotate this back, it would be around here. So if you have your target here, it would, like, realistically, the way this should look, it's something like this, right? And the target would be here. And if you have the target here, it should look like this. Like, okay. And this minimal distance, what it does is, like, if it's less than this distance, the side-to-side calculation fails. So you want to make sure that you're able to calculate this point properly. So that's the way we would calculate that, just a minus b. And then the total length is the opposite, it's just a plus b. That's the total length of the chain. That's pretty easy. And then after we have done all of that, we can say we are ready. So that would be the init function. Now let's move on to the actual function. The draw, nothing special there. We're just drawing circles and lines for the global positions of everything. And we're just abstracting the global position because draw is local. So you wanna just always subtract the global position so it draws in the right place. And as I mentioned before, you have to also have offset for the angle of the parent, but it's kind of like a pain to do that, so I don't use this much, so it's just kind of ignored for now. Okay, now on the process function, if we're not ready, we just return. Then we call update, which as you know, this is just needed for drawing. And then if we have a target node and we are following, we're gonna do the IK algorithm. If not, we'll just do forward kinematics, which is basically just having everything just stick together, like, well, not like that. If I don't follow, we still have forward kinematics, which means that if I rotate this, the rest of the bones follow the chain. And if we are following, then we use that one. So let's set it to follow. And and then the last thing we do is we combine our rotation degrees plus our rotation offset, and we use lerp angle because lerp angle helps us wrap. So when you go, because that's kind of tricky, when you go, if you go from 0 degrees to minus 360 degrees or to minus 180, if you just lerp or if you just assign it directly, you might have like this little like flip, like this glitch, because it has to do like the whole way around in one frame. So you want to use lerp angle, and if you don't want it to actually lerp, you can just use 1 on the weight and it will just be immediate. But here we're using lerp rate, and I'm multiplying by the time scale of the engine because in my game, at least, I use the engine time scale to do slow motion. And if you don't have this, when you're doing slow-mo, the lerp rate is actually super fast, so you want to take that into consideration. Okay, for the forward kinematics, basically you just assign the global position of C, so the start of C to the end of B, and then you do the same for everything. So B goes at the end of A, and A goes at the root. So the start of the foot goes to the end of bone B, and the start of bone B goes at the end of bone A. That's basically forward kinematics. I'm sure there's more to it, but we're not talking about forward kinematics here. Okay, and now we get to the actual algorithm. You could just copy paste this code if you don't want to actually learn much about this. But if you're coming from a different engine that it's not Godot, for example, you're gonna want to like learn the concepts, so you're able to translate them. And if you actually really learn those concepts, you can modify them so they can work the way you want them to work. Especially if you see some mistakes that I made, you can fix it or make it better and let me know so I can make it better for myself. So for the root node, if we have a root node, and the flip vector is not what we already have, just so we're not like reassigning the variable every single frame. We assign the transform xx to the flip vector x. Okay, and we'll see what that's used for later. The target position, we basically just take the actual target global position, and then we just add our offset, and this is the one we're going to use for all of our calculations. The remaining distance to the target is just the bones b end, so the end, so we get the distance to the actual target, and then we multiply by the flip vector. I actually don't need to do this here. I don't know why that's there, but if I remove that, it's gonna work, because the distance is not gonna change if it's pointing here or if it's pointing here. It's really not gonna change, so you could just take that off, but I'm gonna leave it there just to make sure nothing breaks right now. So if the remaining target is less than 0.05, we know we are close enough that we don't want to keep running the function if we are already there, because we don't want to run this code if it's just going to keep calculating the same thing. So we just return. Okay, and then if we don't return, then we calculate the distance to the target. So the distance to the target for the triangulation, as you know, we need to get the 3 sides of a triangle, so we can calculate all of the angles, and we know the length of bone A, we know the length of bone B, and the third side is the distance to the target, so the distance from this root to the actual target, and that's what gives us our 3 sides for the calculation. So if this was a long way out, you have A, B, and then side C would be this distance. So yeah, I think I didn't explain that before, but that's the third side of the triangle that we need to calculate. Okay, the way we calculate the way we do this quick response when we're close, and then this slower response when we are farther away, is by doing these 2 lines of code. So we have so right now we have the lerp range at 100, which is this variable here. So what we do is clamp any value that we have. We make sure that it's between 0 and 100. So if this is at 1,000 pixel distance, this function will basically just turn 1,000 into 100. If it's 500, it'll still be 100. And then if it's between 0 and 100, then you'll get the actual number. So if it's like 50, you will get 50. That's the way clamp works. I'm sure you all guys know, but I didn't know how clamp worked until not long ago. Now and then we get the weight. This weight is what you use when you're lerping. And as you know, or if you don't know, normally when you're lerping, you use a value between 0 and 1. 1 being just getting there immediately, and 0 never getting there, but normally you would use something like 0.1. So if you want to, and obviously there's videos that explain lerp, I'm sure, but basically if it's 0, the lower the number, the slower it is for this to get to where it wants to get. Okay, so what we're doing here is we take our clamped value, which would be a number between 0 and 100 in this case, and then we're just converting that number to be between 0 and our lerp. We're converting the number to be between 1 and the lerp rate we chose. So if we choose 0.1 or 0.2, suppose we chose 0.2, when the distance is 100 or over 100, if it's 1,000 or 500, your lerp rate will be 0.2. But if your distance is 0, meaning you are right on the IK, then your lerp range will be 1, and that's how we get that snappiness here and that like softness here. If you have questions, let me know, but this is what gets that done. Okay, now the direction to the target. I'm using direction to the target instead of using angle to target, because this gives us a normal. and multiplying, I can multiply the normal to the flip vector, whereas if I multiply it directly to the angle, it doesn't really work that well. So that's why we're using direction to. Then we get the parent angle. This is not the same as the root node that we were using before. This is the direct parent. So in this case, we have the leg here. We're getting the rotation of the hip, because as I showed you before, when I rotate the hip, we want the chain to still calculate correctly to the target. If we don't have that there, then if I rotated the hip back, like say 10 degrees up, then the IK would think that the target is like up here. So that's why you need that. Then we get the actual angle. So we just get the direction to the, we get the angle from this normal, and then we subtract the parent angle. So we can just offset that. Then if the distance to the target is less than the total length, so if the target is like within what we could calculate as a triangle, then we actually calculate as a triangle. But if it's farther away, we don't need a triangle. All we need is a straight line, so we can just point at it. So if we are with like less than the distance of the length of the chain, the first thing that we do is we check if the distance to the target is less than the minimal distance, meaning that if it's like here, in this case it doesn't really, I cannot really show you because these two bones are the same length, but I'm gonna shorten it just so you can see what I mean. So if I take this end for, let's take the right leg, and I take the end of this bone, and if I put this 100, so now this thinks that the bone goes from here to here, right? And then we call reset here just so we can recalculate everything. And now everything from here to here is just the sprite, but the actual bone comes from here to here. And now the minimal distance that this could realistically calculate it's not going to be able to calculate all the way to the root, but it should never go past like a point here. So as you can see, when I reach the minimal distance, it stops calculating a triangle, or actually it calculates the triangle, but it calculates it to this point and not to this point. So that's what this is doing. Then we get the angles using our side-to-side function. This will give us 2 angles because we don't need the third one. And if this side-to-side calculation sometimes, and this was my mistake, I was getting nans like on like 1 frame every like millionth frame in one specific animation, and the reason is I was using less than equal for the total length. So when it was exactly the same, this was returning not a number, so NaN or none or whatever. But so I added these checks just to make sure, because it just broke everything. But it shouldn't happen if you have less than, because if this is equal to this, you really just want to point at it. But yeah, you can have this extra check there just so you don't mess everything up. And then this is just like really simple. We just apply the angles, and we lerp angle because as I explained before, you don't want to have like those glitches where it wants to go like the whole way around. And as you may notice here, what we're doing is we are assigning the angle to the target minus the bone's inner angle. So we offset our inner angle configuration. What I mentioned before, if you set your bones to be at a 90 degrees angle, or if you set them to be at 0, or maybe your sprite it's like at an angle, we're basically just taking that out, canceling that out. And then for the first one, we are adding angle B, and you may notice that for the second we're subtracting angle A. And the explanation for this is actually it took me a couple of tries recording this, because it's kind of weird for me to explain this. But when you have let me explain this real quick here. So we have bone A here, right, and bone B here. Now the side-to-side calculation, if your target is here, you can just picture that what you need is a triangle that either looks like this. Let me color it differently. Or you need a triangle that looks like this, depending on the direction that you want. But the side-to-side calculation will not give you a triangle that it's at that angle, but it will actually just give you like a triangle that actually looks something like, what it would look like, it's something like this. The long side, it's just at a 0 angle, so you need to like take that into consideration. And the reason that we add is because if your bone is here, we want to add the angle to the target, which is we're basically adjusting from this angle to this one, and then we're adding this extra bit here, right? But angle A is actually this angle here. So if we were to add this angle, as you can see, if I grab this bone here and I add this angle, as you may notice, this angle, it's like coming here and pointing back. So my bone, instead of pointing like this, it will actually be like this. And if you have doubts about that, you can just let me know in the comments. I might like try to explain it better. And then we just apply, just erase this. Okay, so, and then we apply the weight that we calculated here, so it lerps soft or hard depending on the distance to the target. And as usual, I multiply by the engine timescale, so if I'm in a slow motion part, it will look right. Okay, and then here, if we're just pointing at it, all we need to do is give it the angle to the target and then just cancel the inner angle and you're done. Okay, and then this is the forward kinematic, which actually, in a sense, I could just call forward here, like that, doing the same thing, but I have it like that. If you want it to be more clean, you could just just replace that with the function call, and that's it. That's the whole algorithm. If you have any questions, I know this is complicated stuff. It's complicated for me, so explaining it actually helps me understand it better. I'm not an expert by no means. I've been doing this like no more than 4 months that I've been doing game dev. So yeah, just give me just bear with me a little bit. Give me a little break there because I'm fairly new. I'm just sharing what I've been learning. And then on the next time I'll show you this, all this stuff here, from here to here is helper functions that you don't really use to calculate the IK. It's just stuff that helps with the animations. So I'll talk about this stuff on the next video. I'm gonna do the running animation, adapting to uneven ground, and yeah, hopefully everything made sense, and see you next time.